I love most about my research, I think, is being able to spot trends or spot anomalies in data, and then when we actually figure out what that trend or the anomaly is, and being able to, knit all that information together to come up with a story, or being able to tell the community what we know about our catalysis research. I find that, when you just get that little extra bit of information that you can tell the community about, it's really exciting. Our research sits, I would say, firmly in the boundary between organic and inorganic synthesis. So we are synthetic chemists, and what we try to do is make small molecules that are maybe of relevance to the pharmaceutical or agrochemical industries. But what we're specifically interested in is trying to understand how those bonds are being made or broken through catalyst design. And so we use iron catalysts to undertake those bond making and breaking processes. Our research is fundamental and it's very basic research. And so the impacts, I would say, are more long term, but the Earth is a closed system, and so not being too pessimistic, but we are going to run out of some of our metals fairly quickly, and that's things like the precious metals like rhodium and iridium, and that's because we use them in big bulk processes, but they're also in all of our mobile phones and LCD screens. And so we need to find other ways to make and break chemical bonds, and so that's why we do iron catalysis. Because if we can figure out how to make iron either behave as a precious metal or do reactions that the precious metals can't do, then we've sort of filled a gap which will hopefully help society in the long term. There's two main streams in my research programme, iron catalysis and phosphorus chemistry, and sometimes those areas overlap. But a major focus is iron catalysis, where we're really looking to try and do sort of smart catalyst design. And so a lot of the students in my group will be synthetic chemists, but they'll also be trained in other techniques. So a lot of the students do their own computational modelling. That's usually with a collaborator who is an expert in computational chemistry. But also using other techniques, different types of spectroscopy, such as EPR, Mossbauer, and really advanced mass spectrometry techniques. And so not only are they going to be a really good synthetic chemists, but they can, I guess, use those skills more widely as they move beyond their PhD. But it also gives us extra knowledge to really understand catalysis more, because iron doesn't behave like the precious metals, so you need to pull together lots of different bits of information to find out as much as possible. It's very collaborative, so we've got collaborators quite widely in the UK, because some of the kit that we need is very specialised, so there's maybe only one person in the UK that has the kit. In terms of computational chemistry, we collaborate with Professor Stuart McGregor, who's up in Scotland, and Professor Vera Krevald, who's at TU Darmstadt. And they both have their individual expertise in computational chemistry and really help augment our understanding of catalysis. I think it's really important to celebrate, research achievement by getting, work published. And so whenever someone publishes a paper, and it doesn't matter what the paper is, where it's gone, we always have group donuts. Before we moved to Cambridge, I lived in Bath, which is a beautiful city as well, but it's so hilly. And so one thing I've enjoyed about Cambridge is riding my bike on the flat. And so I feel like I've really embraced Cambridge life just by how often I've ridden my bike since I've been here.